Great to have you on. Go through how nerve-wracking this entry and landing was. Speak to the challenges, because I think 40% of these have failed. This one did not.
It did not, Michael, and we are so relieved. You know, when you see us cheering and getting so excited, it's not that we're just happy, just we're relieved that we didn't forget something, because these are so complicated. Landing on Mars is a strange combination of landing like you do on Earth as well as you do in the moon. It's because Mars has too much atmosphere to land like you do with the moon. We just fire rockets backward, and it's too much atmosphere too little atmosphere to land like we do on Earth with a parachute or wings. And so that's the challenge we have. We've had to kind of glue these two landing architectures together in a Rube Goldberg contraption that actually gets us safely to Mars in only 6.5 minutes.
Who figures that out? You, I suppose. I mean, that's complicated stuff. I mean, there's a lot of trial and error, I assume.
There is, and a lot of it was figured out in the early 60s. A lot of the designs that we've used today were based on the original, both Soviet era and U.S. Mars landings. But a lot of the changes have occurred, especially in the part that actually does the end part where we land. Some of our landers have used airbags and solid rockets to come to the final stop. Others, like Viking, use throttled engines that you can control to land slowly on the surface. Others still use pulse mode rockets like this one did today. The Phoenix lander landed a few years back, did the same kind of pulse mode landing. And of course, there's another kind you remember is the Sky Crane architecture, where we lowered Curiosity rover to the surface of Mars in 2012. So we have this diversity of designs that my team members and I have to use in order to, depending on the payload and depending a lot on where we're trying to go on Mars.
Well, we'll speak to that too. What makes this this different in terms of the aims? It's not all about the surface, it's about going below the surface. Why, and what do we hope to get out of that?
Well, you know, Mars is an amazing place. It's between the Earth and the Moon in size, but it's had a very strange history. In many respects, it's like a museum of the way Earth, the surface, the way Earth was billions of years ago, because as you know, plate tectonics and erosion changes our surface. So the surface of Mars is almost frozen. Yet, ironically, the inside is also seems to be frozen, but not completely. As you know, the moon seems to be cold and dry. There's very little in the way of moonquakes. But Mars, we think, still has a residual core like Earth does. It does not have plate tectonics, and we don't see volcanism today, but we'd like to know what's going on inside of Mars. Does Mars still have a magma? We know it's got a very tiny magnetic field, but is it possible that that field is still there, churning on its own due to rotation of iron-like fluids? We'd like to know more about that, because in many respects, the story of Mars is, in some sense, a part of the story of Earth.
We're nearly out of time. We're up against it, but I did want to ask you, for those who sit out there and go, wow, that's a lot of money to spend, why do we care?
Well, you know, when we go out to these places, we are not just learning about our own world. We're learning about how to think about a world in a larger context. And in fact, if it wasn't for our studies of Venus, we would never have learned about the prospects of a greenhouse effect that could trap heat. We learned by studying Venus that gases like carbon dioxide can trap heat inside our planet too if we let it build up too much. And in fact, that's exactly what happened. So by looking out to the other worlds, we can ask questions about our own world. And in fact, we can ask questions about, is life that's so common in this planet, is it ubiquitous outside of this planet? Is it ubiquitous in the solar system?